In the Ice and Rain series of lessons, we will examine the methods used to detect when an aircraft is flying in icing conditions. And we will look at the various systems that can be fitted to aircraft to prevent ice and rain becoming a problem. We will not be discussing pre-flight ground de-icing. This is covered in the Operational Procedures series of lessons. In this lesson, we will first quickly look at how ice forms, and then we will look at the various systems that can be used to detect icing conditions and give a warning to the pilot. Icing on aircraft in flight is caused primarily by the presence of supercooled water droplets in the atmosphere. If the droplets impinge on the forward-facing surfaces of an aircraft, they freeze and cause a build-up of ice, which may seriously damage the aerodynamic properties of the aircraft. These droplets can exist in the temperature band from 0 to -40 degrees Celsius. Below -40, they are already frozen and will not stick to the surface of the aircraft. The actual amount and shape of the ice buildup depends on the surface temperature and the size of the droplets. A full explanation of icing conditions is given in the Meteorology series of lessons. You should expect ice to be a problem whenever the temperature is between 0 and -40 degrees Celsius, and visible moisture in the form of clouds or rain is present. Ice detection systems can be split into two groups: those which sense a build-up of ice, known as accretion-type systems, and those which sense by measuring temperature and humidity when icing conditions are present. These are known as inferential-type systems. The simplest of the accretion-type detectors is the pilot's eye. He may be able to see ice beginning to build up on such things as the leading edges of the windscreen wiper blades. Some aircraft may have lights to illuminate the wing and fin leading edges, plus the engine intakes to help the pilot monitor for the build-up of ice at night. On some aircraft, the pilot's eye is the only ice detection system. To assist the pilot, some aircraft have a device known as the Teddington ice detector. This detector consists of an aerofoil-shaped mast protruding into the airflow, which is visible from the cockpit. The mast incorporates a heater element and a light to illuminate the mast at night. When icing conditions are encountered in flight, with the heater power supply switched off, ice accumulates on the mast and gives a direct visual indication of ice accretion. The heater may be switched on for a short period to dissipate accumulated ice. The more quickly the ice reforms, the more severe are the icing conditions. The Smith's ice detector is another accretion type of detector. It consists of a hollow tube, attached to the aircraft by one end, sitting in the airflow. It has holes drilled in the leading and trailing faces. There are 4 holes in the leading edge and 2 in the trailing edge. In flight, under normal conditions, the air enters the 4 front holes more quickly than it can exit by the rear 2. This causes a pressure build-up in the tube, which is sensed by a capsule connected to its base. The capsule expands, keeping a pair of electrical contacts apart. In icing conditions, the leading edge holes become blocked by ice, and the pressure in the tube falls. The capsule contracts, causing the ice warning light to illuminate. There is a heater element fitted around the tube to melt accumulated ice. Once again, the more quickly the ice reforms, the more severe are the icing conditions. The English electric or Napier ice detector is a mechanically operated accretion type of detector. In this detector, a serrated rotor shaft is continuously driven by an electric motor. The shaft rotates adjacent to a fixed knife-edge cutter, with a clearance between them of less than 0.02 of an inch. The unit is mounted on flexible mountings on the side of the aircraft fuselage, with the rotor shaft protruding into the airflow with its axis at right angles to the airflow. The cutter is in the lee of the shaft. Under normal conditions, little torque is required to drive the rotor. In icing conditions, ice builds up on the rotor and is shaved off by the cutter. Shaving off the ice requires greater rotational torque and causes the motor to rotate slightly in its flexible mountings. This movement operates a microswitch which gives an ice warning. The warning remains as long as ice continues to foul the cutter blade. The rose mount ice detector is another mechanically operated accretion type of detector. It consists of a short cylindrical probe positioned in the airflow, mounted on a vibrator housing which vibrates the probe axially. If ice builds up on the probe, the added mass reduces the frequency of the vibrations. When the frequency falls to a predetermined level, an ice warning is given. When the ice warning is given, a built-in heater element heats the probe, which melts the accumulated ice, allowing the vibrating frequency to return to normal and the warning to stop. After 6 seconds, the heater switches off and the icing cycle recommences. The frequency of the cycle may be measured to give an indication of the ice accretion rate. The final accretion type of ice detector that we want to look at is the beta particle detector. This is the most modern type of detector. It has no moving parts. The detector consists of 2 probes, mounted perpendicularly from the forward fuselage. The forward probe is an emitter, which emits beta particles. The rear probe is a beta particle detector, which detects the level of particle transmission from the front probe. Beta particles are absorbed by ice, so that, in icing conditions, fewer particles are sensed by the detector. At a certain beta particle count rate, corresponding to approximately 0.4 mm of ice, a relay in the detector probe will operate, causing a warning on the flight deck. Ice can only be formed when there is a combination of moisture and freezing temperatures. In the Sangamo Western ice detector, these 2 conditions are detected separately, and therefore icing conditions are detected rather than actual ice formation. This then is an inferential type of ice detector. The system comprises 3 main components: a moisture sensing head, a moisture detector controller, and a thermal switch. The moisture sensing head consists of 2 heated metal resistance bulbs situated in the airflow, and arranged so that the leading bulb screens the rear one, in such a way that no moisture impinges upon it. When the detector encounters moisture in the airflow, the shielded rear bulb remains dry, and cools at a slower rate than the wet leading bulb. The moisture detector controller is situated in the base of the unit, and senses the temperature difference between the wet and dry sensing bulbs. When the temperature difference reaches a predetermined value, it will send an icing conditions signal. The thermal switch is a contact operating thermometer which is housed in a bulb and is exposed to ambient temperature. With a temperature below freezing, the thermal switch will send an icing signal. If both the moisture detector controller and the thermal switch are sensing icing conditions, then an ice warning will be given, or the automatic anti-icing or de-icing cycles will be initiated. That is the end of the lesson on ice detection. You have seen that there are two types of ice detector. The accretion type, which senses actual ice buildup, and the inferential type, which senses when the aircraft is in environmental conditions where icing will occur. You will find that on many modern aircraft there is no ice warning system, or perhaps just the Teddington type of visual indicator. So an awareness of the in-flight conditions with regard to temperature and moisture is essential for all aircrew. In icing conditions, the first signs of ice buildup can usually be spotted on aerials or on the windscreen wipers.